on the bottom, sigma 2, x map to false. Right? Because these are equivalent states, given x is high. Now I'm out of sync. Right? So this one goes to C1, that one goes to C2. Where do I deal with this somehow? So now my setup allows me to actually deal with this, to know that, oh, I'm temporarily splitting, but let's say that the full command is actually after this if branching, you have C3, right? So that's actually my real program. Somehow I have to tell the system that, yeah, temporarily branching is okay, because eventually I'll be done with this. When I'm done, I'm going back to the same command. I'm in sync again. I need to do that somehow. Also, when I'm out of sync, this one evaluating C1, that one evaluating C2. If you think about traces, the first trace, I have a bunch of C1 executing. The second trace, I have a bunch of C2 executing. Initially, I have sigma 1, sigma 2, that they're equivalent. At the end, this goes to sigma 1 prime, this goes to sigma 2 prime. Why do you think these two can still relate at the end? What's the argument why this, initially they were relating? They're executing a bunch of different commands. Eventually they finish, right? They get to here. Why do you think this will still relate at the end? What's the reason here? This is another key part of the, like what our type system allow me to actually get this relation later on. Yeah.
Since the Boolean variable is high, they should both have a high C, or the Boolean variable is a, yeah.
Yes.
So then they're still both, everyone is operating with a high.
Yes. So basically all the assignment I have, this one might assign Y, that one might assign AB. But type system makes sure the only variable I can assign is actually high variables, right? So the difference between these two will be okay, because when I define store equivalence here, like going back to value equivalence, if I'm modifying high variable, I don't really care what updates. It's okay, I'm still going to be the same, right? Yeah. Okay, so these are the pieces, but the problem is I don't have enough machinery to build out. My intuition tell me that this is under high context. Now my semantics tell me where the high context lives, right? So next I actually need to fix that. So one proof technique, typically whatever you need, your semantics doesn't have it, you can add it. Those are for proof only. So what I will do is, again, do a little bit of cheating. When I have if statement, I'm assuming I know the label of this if statement, right? This is not, sorry, writing is very hard. So this is just harmless labeling up here, right? The type system can tell me, right? So I can also, if the label is given by programmer, I can also check labeling correct or not. So I'm going to have this labeling up here. And then for me to keep track of context, I already have something to keep track of context, right? So basically what I want is I want to double this context so that I can actually keep track of label here. Right? So when I have label, it meant the current command is executing under this label that I'm waiting for, right? That means I want to have if statement. What's my if? If it's here, right? When I go into C1, I actually need to take a drawing. Because initially, while I'm waiting for C1, the context might be low. Now I'm under branching, I have to fold this in. So I have to define, I'm going to overload this drawing. I'm going to have this label joined with S, right? So the definition of this is that if I have a hole with original label, I call it old label, on top semicolon C, on top of some other S, if I take another label, which is PC, join with this, this will give me a context with the old join this C. I don't care about anything else, right? Because once I'm done, this will be popped. I don't push label down anywhere else. I'm going only to push label after the first hole. Right? So now I have context now. Right? Now I can speak of, hey, when I execute to the point where there is a C1, the hole inside S will tell me this is the high context. That will allow me to define the sigma being equivalent, sorry, this big sigma being equivalent, accounting for the differences. All right, so I do have all the proof written out. Let's see, so these are scribbles. I'm gonna try to spend the next couple minutes actually write this out because we'll build more. This will go up if I put this down. I have to push it up. Okay, I'm just writing out, trying to write this out and figure out how to actually define this. On the other side, I have sigma 2, stack 2, and C2, right? I want to somehow define these are equivalent given gamma. So the piece I know about is how to define this, right? So now I have to say, how do I define these are equivalents, right? So any thoughts on how we might want to do this? At a high level, I want to say something along the lines of S1 gamma shows. Do I need gamma? Maybe gamma, I need gamma. Let me check my notes. This somehow is low equivalent to this S2, C2. Somehow I want to define that. Accounting for the fact that some of these commands may not be the same if the context is high. So in range flow security, one trick is a lot of times what we define is a projection relation to remove anything the attacker can't see, right? So this applies to here as well, right? So I can actually, if this is high context, I can remove this. When I check these two, once the high things get removed, the rest will be the same. So that's the intuition of me defining this equivalence. Right? So I'm going to just write this out. Given the constrained time, we'll find my notes first. Okay, so I'm going to define projection. So this is defined as if the projection equal. The goal of the projection is to remove anything high that attacker can see. It doesn't matter the branches, right? So I'm just going to, again, this is going to be induct over the structure of this. Right? I actually don't think I need gamma, now that I'm thinking about it. Right, so let's see. So if I have, if the empty case is easiest. Maybe let's start with empty. Easy case. If I have empty, so I'm always going to start empty with my lowest label, right? So if it's empty with a C, I project this, this will just give me C, basically, right? Because this context is bottom, the C is a command running in low context, but I should have the commands here, right? So now I can do the inductive case where I'm going to have some label with a command, that's called C1, and then here another command, this is C2, I won't project this, right? With LA, this LA. Let's see. Yeah, because I'm looking at LA, I'm trying to look at this. So the label, the context C2 run under is in this L. I'm trying to decide to surround this C2 or not, right? So decision is based on comparing these two labels, right? If L is lower than LA, that means that the attacker can see this, right? In this case, this is just going to be, I think it will end up being, let's see. Yeah, so in the end, the result is actually, let's see what's on top of S, missing this. So then I'm just going to, this This means that this command is visible, right? So I'm going to fold this command together because these two used to be a pair, right? So this is going to be S with C2 semicolon C1 projection to LA. Right. So I've decided that this is lower. The attacker can see this. So I'm going to return this command to its original form. And then I'm going to look deeper inside the stack, right? Because this is like, I pulled out all the semicolons, the sequences into this, so I need to continue to look at lower on the stack, right? Yeah. We'll write out the other rules so that we can ask questions and stare at this. So if I have a hole with some command 1 on top of S, and then another command 2, I try to project. So here, this L is not lower than LA. That means that the attacker can't see this one, right? So I need to throw this one out. Therefore, this projection should be S with, this should be thrown out, so only S1 is left. I'm going to project LA. Right. So, does it make sense? I'm trying to remove the part the attacker can't see. The command doesn't matter, right? So now what you can try is that the cases up written on top where the branches on the high start to split, the projection remain the same. Doesn't matter I split, right? On top, I want to see 1. On the bottom, I want to see 2. But the projection here are the same thing. There's a box. This condition hold. I'm throwing out the other piece, right? Yeah. All right. So now we can sort of have everything we needed. What we need are these one-step lemmas, right? We need to say when I take a step, what should happen? So there are 2 cases. One is I'm taking quote-unquote a low step, meaning that both configurations are under low context. They are taking a step. The other case is one of them have a high context. Right, so I build out lemmas. This is also called a unwinding when you do information flow proof. Your theorem have multiple steps. You also have to pull them back into low step and high step. Right. So when I have a lemma, so this is like a low 1 step. So basically saying is that if sigma 1 is equivalent to sigma 2, somehow I have to define that sigma 1 has a label such that this label is lower than LA. If that's the case, and also I think both sigmas, sigma I with I 1, 2, by twice. If that's the case, basically if, I think because the way I phrase this, we can say that if sigma 1 makes a step to sigma 1 prime, sigma 2 make a step to sigma 2 prime, this implies that sigma 1 prime still going to sigma 2 prime. So this low step lemma, so if I have 2 configurations, if they are both low and they're equivalent, they should make the exact same matching step, and the resulting configuration still remain equivalent. So I intuitively said there's low. So where do I get this label from the sigma? How do I know this is low? I'm executing commands under low context. Where do I get a L? Inside my sigma. The whole, right? So here, in this S, when I look at the S here, I actually going to look at this label, right? Say that this is my S in the sigma. If this label is lower than the attacker's label, this means that this command is executing under low. If this label is not lower than this high context, right? So I can define this property. So I have you guys check this out, right? This is a low step, but then the next 1 step is the lemma is a high step. It's called high 1 step. So for low 1 step, both of them make a step, and they're the same, right? We also have actually, when you're proving this lemma, you actually have to prove if they're low equivalent, we end up having the same configuration. That's the lemma you will prove later. But for 1 step, for high 1 step, so if I have a sigma that's actually high, that have L where L is now lower than LA, for this case, it doesn't make sense for me to compare with the second trace because they already not the same, right? So typically what we do is as we were discussing, if you're in a high step, if you're stepping by yourself, you're only going to modify the high memory. So typically what we do is we're saying, if this one, no, if sigma make a step to sigma prime, then actually sigma here can use gamma. Actually, the resulting state is going to be low equivalent to the original state, right? Because if I'm in high context, I'm never going to modify any low variables, right? So if I look at two traces, so what's going to happen is that we'll say that I'm going to draw circles as my traces now. And on the bottom, you have another trace. So when I induct over, this is n step, this is m step. When I induct over this, I start with low, right? So the induction hypothesis is that if these two are in low, then they both can make a stack. Then I can apply induction hypothesis on the rest, because now I'm going to look at n minus 1, n minus 1, right? That's a low case. I'm going to apply this low lemma. In the case where one of them is high, I'll stack one of them, right? I'll go to this state. Because these two are low equivalent, this relation is transitive, therefore these two are low equivalent. Therefore, I can do inductive hypothesis on these two cases, which is n minus 1, n. It's still smaller, so I can still apply inductive hypothesis. In the case, this is low, this is high, except this one, right? So then I do inductive hypothesis on n and n minus 1. And these are three cases. We can end up tiling our one-step lemma together to try to get to this. Yeah. So that's a super high-level picture representation. So the slightly tricky part, I think I'll skip that today. Probably you can, I can assign this as homework. Actually, try to prove the one-step low. You will figure out that somehow intuitively, as we were building out the context, if I'm looking at the sequence of labels in my stack, intuitively in your mind, so say that this one configuration on top of another configuration, so on and so forth, it seems to make sense that once this is high, anything above should be high, right? Because I keep joining label. It shouldn't be the case that somehow, somewhere down here, I have went to low, and somewhere here I went up to high. So this somehow shouldn't happen, right? So this is an invariant we can actually prove inductively. Also, you would actually need this fact when you prove this one-step lemma. Right? So if you're interested, try this out, and you will figure out why you actually need this. All right, so I'm going to stop here. Because doing proof is always a lot. The best way to actually figure this out is complete something. So this will be the nice one to complete. The high one, we already kind of eyeballed it to see if it makes sense. All right, any questions?